Okay, we're ready to roll. Okay, so that's the homework. If anybody has any questions about that. Okay. Okay, so next on our agenda is atomic structure and transitions. No class on spectroscopy is complete unless you understand the processes that modify light or release light. Okay, if you've got light acting in a gas, you know, there's the one thing about how the photons balance the conditions in the gas. There's another about the light that actually makes it along your line of sight that you observe. So part of this class is first going to be understanding how that light interacts with atoms and how atoms then will release light. We've already talked about it generally, and what we have said is that there are things called bound-bound transitions, and there are other things called bound-free transitions. Now, bound-bound is from bound state 1 to bound state 2, and a bound-free is from bound to free. Later on, we're also going to talk about electrons that are free coming into being bound, what we call free bound transitions, also called recombination. You know, a recombining of the electron into the bound state with the atom. All right. There are also other things called free transitions, where it's a three-body collision where if you have an electron that's free, that's near another atom, and a photon comes through, the photon can be scattered or some of its energy absorbed and into the electron, which would raise it to a higher energy state, higher velocity kinetic energy. Photon and electron will not otherwise interact apart from simple scattering, but the photon energy is not changed in a simple scattering of a photon. This bound or this free transition requires angular momentum to be absorbed by the nearby atom, so they call it free. We'll get into it later, but those are the main things. We're also going to only study basically atomic physics because the spectra of vast majority of the universe is based upon atomic physics. Okay, we're not going to really study molecular structure in any detail or molecular absorption or emission. I will leave that up to Renee, who teaches the interstellar medium. Okay, so stay tuned for that. All right, so what do we have? What's on our list is hydrogen atoms. We're going to start with Dr. Bohr. Okay, now this should be a cartoon model which is firmly planted in your brains already. Then we're going to move to Schrodinger's wave model, which is still terribly wrong, but useful. It's the obvious transition from semi-classic to the wave. But then we're going to get into the Dirac model and talk about something called fine structure. Now I'd like to ask you, you all had, I'm imagining, a quantum mechanics class before you came here. Okay? And in that quantum mechanics class, I'm hoping that you at least studied the Schrodinger atom in some detail and understand the wave functions and what gives rise to those wave functions to some degree. And that it gave basically the same energy levels and bound states as Bohr. Did anybody learn anything beyond that? Did anybody learn about Dirac's model of the atom, where he took Schrodinger model and added special relativity and electron spin? Schrodinger model does not include electron spin. Okay. So it's incomplete. A lot of people get out of their undergrad in physics or something like that. They think Schrodinger model is kind of like it for hydrogen. Now, it's as incomplete as Bohr was, except that it's firmly quantum mechanical. So we have to talk about that next model, the Dirac model. You can't really understand atomic spectra unless you have a better feeling for something called fine structure. Okay? For example, when you think of the Lyman alpha line, you probably think it's a single transition. I got news for you. There's fine structure and there's splittings in the n=1 state, and Lyman alpha is actually a doublet. H alpha, you probably think, well, that's a single Gossamer Finn 65, 63 angstrom photons coming from an energy change of n=2 to n=3. And it's a single, if I had a super infinite resolution spectrograph, it would be a single line. Nope. It's actually made of 7 lines. All fine structure. Maybe you heard it here first. I don't know. Okay. But by the time you're done here, you're going to understand the H alpha transition way better than you did before. And maybe, I'm hoping, better than most people that get out of grad school, because I'm not sure, like, for example, I didn't understand this when I got out of grad school. Again, I'm trying to teach a course that I feel, I'm hoping, teaches all the stuff that I wish I had been taught to do my science. Okay. In this process, we're going to talk about something called a damping constant, an oscillator strength, and something called selection rules. We're also going to introduce quantum electrodynamics, because it turns out that even Dirac wasn't all the way right, and it turns out you had to quantize the electromagnetic field as well before you got the full tomato, okay? And that involved quantum electrodynamics and radiative corrections, which cause small energy shifts. In order to get the exact wavelengths right, the exact energy changes of the bound states right, you have to introduce something called these radiative correction shifts. So anyway, I'm going to introduce all those to you, and then we're going to get beyond hydrogen. Hydrogen is so simple. We're going to get into the multi-electron atoms. And again, I think I'll be showing you stuff that you just wouldn't pick up unless you picked up a nasty book on your own. Hopefully my book notes aren't nasty. We're going to talk about isoelectronic sequences and really truly understanding the periodic table. Now, all of us have seen the periodic table. We have some understanding of it. I'm hoping that I'm going to have you see it in ways you hadn't seen it before. Okay. And then we're going to talk about where do you go to get the best new information if you want to do spectroscopy and I want to find out what is the energy state, what are the transition wavelengths, what are the oscillator strengths and damping constants of, of say carbon 2 excited state, blah, blah, blah. Okay, I'm going to go to the National Institute of Scientific Standards, and they have an amazing webpage. Okay, so, and then some common stellar transitions, which are not in my book notes, but are in my handwritten notes. Okay, so are you ready for this adventure? Now, I haven't ever taught out of my actual book notes yet, so we'll see how it goes. If it doesn't go well, I'll go back to my handwritten notes. We're just going to give it a try. But I was looking at them last night and thinking to myself that we should be fine. Okay, we're going to start with the Bohr atom. Okay. We're going to start with the Bohr atom. And that atom came around in 1913. It's semi-quantum mechanical in nature, all right? And basically he had 2 postulates: circular planar orbits about the nucleus, total angular momentum must be an integer number of the Planck's constant. You've probably seen this before. And an orbital electron is a stationary state. It's stable, and an atom emits or absorbs radiation only when the electron changes states. Now that actually was a postulate that was in opposition to everything that was known about physics at the time. So here was this young 22-year-old Dane, and he basically made postulates that he could have been laughed off the face of the planet for by all physicists. He stepped out of the box, he took an example, but he worked out the implications of these 2 postulates, and nobody could deny how correct his model was for the time. So here's his stipulation that the angular momentum is a integer number of Planck constants. Okay, so when you get that, you get this nice little relationship that the reduced mass times the angular velocity times the radius squared for state n is n times h bar. Okay. Now, it's very important that you use the reduced mass because in Bohr's model, which they don't really teach you in sophomore physics, they always say the nucleus is, there's the infinite mass nucleus approximation is what they show you. But in fact, there is a center of mass that the electron's going around and the proton is going around. And so you have a reduced mass, okay? And that reduced mass, if you do the calculation, is the electron mass divided by 1 plus the electron mass over the nuclear mass. So electron mass, nuclear mass ratio in the numerator, 1 plus that. So basically this is a number very close to the electron mass, okay, but it's slightly smaller, okay? So basically you're saying the angular momentum of the reduced mass of the electron, and I use those at n caret. That's the reduced mass of the electron, is a number, it's about 99.98% of an electron mass. Okay. So in his model you have these orbits, bound states, okay, n equals 1, 2, 3, 4, 5, and actually these are to scale. This first orbit is called a Bohr radius. It's about half of an angstrom. Right. When you work out the energies, you get the energy of state n is basically the electron charge squared times the charge of the nucleus divided by 2 or half of the radius of that state n. You can do some math to determine what the radius is. It is basically the Bohr radius, which is, like I said, about half an angstrom. Okay? And that Bohr radius mathematically is h bar squared over mec squared. I love that. Think about that for a second. mc e squared, m, mass of electron, c squared. Oh, e squared, sorry, e squared over h bar. Okay. So this Bohr radius, okay, n squared, Bohr radius n squared over z, and then this is just correcting for the reduced mass of the electron. If you did the infinite mass, then this ratio is 1, and that would be what you get. But because you're accounting for the reduced mass of the system, there's a factor of about 0.99946. Okay, that ratio is 0.9. It was 99.916% of the electron mass. And for helium, it's 99.986%. So what a lot of people do is they define something called the reduced Bohr radius, which is the ratio of electron mass to the reduced mass of the infinite mass Bohr radius, which is given by this number here. And I believe that should be, yes, there's a hat over it for reduced Bohr radius. Okay. So basically, I'm introducing to you the fact that you do get something called isotope shifts, because if the mass of the nucleus changes, then the radii of the orbits change, the energies of the orbits change. Therefore, the frequencies and wavelengths of the photons for different transitions are different. So I'm introducing you this reduced mass notation because later on I'm going to talk about isotope shifts. Okay? Okay. If you go through the whole ball of wax, you can calculate the energy of state n. You know, there are multiple forms of it. Pick your poison or pick your weapon. I like the last one at the end. First of all, I want you to know something about this energy. It is negative because the electron is bound. look at this, mc squared over 2, half of the rest mass energy, central charge alpha squared over n squared, okay? Where alpha is c squared over hc, e squared over hc, which is what's known as the fine structure constant, okay? And then the reduced mass ratio. So it's either this thing with the z squared over n squared and, you know, me fourth and 2h, or it's e squared over 2n times z squared over n squared, or you can think of it as half the rest mass of an electron times the fine structure constant squared over n squared. I love that. And why? Because we're going to find out later that fine structure are powers of alpha. Okay? And so alpha is going to, that's why it got its fine structure constant name. And we're going to find out that these various splittings are a function of various powers of alpha. Okay? Where alpha, again, is given by e squared over hc. H bar c. Okay. You've heard of the Rydberg constant. Okay? We're going to define that. This is the infinite mass Rydberg constant. Okay? Electron mass e to the fourth 2h bar. It's basically this thing in front of the z squared over n squared. Or it is e squared over 2a naught. Basically the thing in front of